Hello ladies and gentlemen, and welcome back to GGS 300. So this is the second week, and today we're going to be working on the second laboratory session. It's really the second laboratory session where we're actually kind of getting into, the actual meat of the course. Essentially, in the first session we were just basically installing R and making sure that you guys were hopefully all up to date with where you need to be. Before we begin the actual lab, I just have a couple of slides that I want to share with you, which I should probably have shared with you last week, but it's just kind of very basic introductory work, particularly for how you might want to kind of solve a problem when you basically inevitably come up against something which is happening on your computer which you can't solve. Okay, so you have the option, if you don't want to install it on your machine, you have the option to use Gmu Virtual Lab. You have the details for how to do this here. Obviously, I've opted to use open source software for this course, so I hope you won't need to use this, but you can if you need to. As I said before, you could install RStudio. We walked through this last week. Hopefully you're able to install that on your machine as well as an actual version of R, the language, and then you're able to basically get going with using the software. You do need to download the actual code for this laboratory session. So if you go onto the Blackboard website, so the MyMason website, and you go to GGS 300, there will be in the course content the laboratory code, and basically there'll be a video there along with it, and you'll be able to, I assume you've already found this given the fact that you're tuning in now, but you'll be able to download the code and you'll be able to save it to a working directory, open it in R, and basically you should be able to get going with the code that I have here. Okay, so you need to navigate to the file tab and then open the file where your code is stored. So the key issue of this presentation is just really to kind of emphasize what you need to do when you get stuck, and it's going to happen to all of you. It's part of programming, it's part of understanding how to do this course. It's frustrating. I mean, everyone kind of has like a love-hate relationship with programming. I mean, it's just such an amazing thing when you're able to do it, but you obviously have all of those kind of bang your head on the desk moments where it's, not going very well. So that's a real challenge. But what I will say is that the number one thing you need to learn is when you have an error message which is produced because of some code you've written in R which isn't working, is you need to copy and paste that error message and put it in Google, okay? And Google will essentially produce a list of different answers for basically everyone else in the universe who has already had your problem, for which in pretty much every circumstance that you will be working with, there will already be a vast quantity of information on the internet describing how to solve your issue, because really we're just going over kind of basic stuff in this class. Okay, so what I would like to advise is that when you get a recommendation for a question and answer, when you've put that into Google and it takes you to Stack Overflow, that you follow it there, because Stack Overflow is this wonderful resource where you can ask a question and other people will basically come and answer that question that you have and suggest solutions for solving that problem. And you can read those through and hopefully you'll be able to work out the problem which you have yourself. Okay, so if you take a look at Stack Overflow, you're able to follow it through. You can see all these questions here, and then you can just you can just search in here. So let's say remove white space from data frame. Let's just say that that's the problem which you have. Once you've done that, you can basically go into a question like this. It's got over 1,000 upvotes. There's an answer here which has got over 1,600 upvotes, and it describes how you do that process. Okay, so you can just read there what you need to do in order to work out how to solve your problem. How do you ask a good question in Stack Overflow? Well, it's probably worth you reading this before you actually get into the content and try to post something. Really, you don't want to post something that is hard for people to understand. Okay, so and there's some kind of standard ways that you need to kind of word your question. You need to make sure you've looked at whether anyone's asked it before, for example. So you need to basically read this before you begin. Okay, so just follow this briefing that I've shown for how you basically ask a good question. Make sure you produce a reproducible answer example so that someone else can literally reproduce the problem that you have. So you've got all of that material. I'm not going to spend too much time going over it because we do have quite a bit of content to cover today. So I'm assuming that what you've been able to do is download the code. So you need to basically download the code from Blackboard and put it in a specific folder. So here, like I'm in my Dropbox. I'm able to go to teaching. I'm able to go to the module I teach, and I'm able to go to the version that I have for this semester. I'm able to go to week 2, and then I'm able to go into the laboratory session where I have my code. Okay, so this is the code that you're going to have. It's called Lab 1, and once you've opened it through that file there, you just click Lab 1, and it opens it. Okay, so hopefully you've all been able to do that. I do list the instructions for you here, so that should be fairly clear cut for you. What I will say is that you see this hash, this pound sign here, this is used for commenting. So if I just type like this, you can see how it's black. Well, if I actually put a hash, then this text is not used by. So basically, once it's actually hashed out like this, R will ignore it, okay? So you see the hash happening here. So it's not actually providing anything to R. So if you use the hash like this, then it just means that you're able to write throughout your script, which is really handy. I know some programmers, and they would always say that at least 50% or more of your code needs to be notes and comments like this, so that you know exactly what you did in it. And that's really good practice, actually, because what it means is when you open it 6 months later and you've forgotten everything in the code, you know exactly what's happening and where you got things from. So do write notes, it's really important. So the second note here is that you can just type commands into the console. So I can type print hello world here, and it will basically take that command and it will print back out what I told it to do, which was the hello world. Or you can just write it up here in this scripting file that we have. Okay, so if I press Control Enter here, then it runs that. You could also just press run, see the run button up here within this script that we have, and it will just basically print that down in the console. Okay, so I like to use Control Enter, which allows you to just do it really quickly without needing to kind of use the mouse to go up here and find hello world, find the run button. Okay, so I think that that's fairly straightforward. Let me just write that note in there. I think that's going to be easier for you actually using the hotkey. So it's Control plus Enter, and then you'll be able to run that. Okay, so we've got the scripting box just here, which holds your scripts. You're able to save stuff here or run it. You've got the console down here, basically, which is just basically saying, it's letting you know exactly what you've run, you've told R to do, and it's giving you an answer. This is the environment up here, the actual memory that you have, so you're able to put things into your working memory, and it's able to basically store that information for later. Then you can look at files that you may want to load. You can plot specific graphics, so you can produce graphics basically. You can go and look for new packages that you might want to install manually. You can look at the help menu, and you can also view anything that you may want to look at. Okay. Now I'm not going to get too much into this because most of what we're going to be doing is we're going to be running our studio through this scripting command line. Okay, so you can do it all manually over here, but we don't really want to do that. We want to make sure that we have everything written explicitly in the code. So our commands have 3 different types of components. So firstly, we have an expression. So this is an algebraic expression. So it's a number, a variable, a function, or some other combination of symbols that can be connected by some sort of mathematical operator like addition, subtraction, multiplication, division, exponents, or roots. So here, basically, what we have, if we have 2 plus 3, I can press Control Enter, and that's obviously going to print 5 as the result. in the console down here. So we've told R to add 2 plus 3. We're also then able to kind of run this whole expression here, which as a result of BODMAS, so brackets, operators, division, multiplication, addition, subtraction, is going to produce 38. So it's going to do the multiplication first, so 3 times 12, it's going to be 36, and then 2 plus 36 is going to be 38. Okay, so it's fairly logical how it's managed to produce that answer, 38 down here. If you do want to produce different results, then you need to make sure that you add your brackets in there. Okay, so if we go 2 plus 3, which will be 5, 5 times 12, then we're going to end up with 60. Okay, so that should be fairly straightforward for you. You can write anything in there. You are able to use any of the multiplication, division, addition, subtraction operators that you have at your disposal, which are numerous. Okay, you can literally do whatever you want. So that's the first example of expressions. You can also use assignment operators. Okay, so essentially what this is you can see this arrow that we have just here. You can also use an equals if you would like, but basically the presence of this operator creates an assignment statement, which basically means that x is basically equal to 2 plus 3 times 12. Okay, so a variable is given on the left. It's a bit like when you write out a math equation, and the expression is on the right, and the expression is calculated, and then the result is stored in the memory. So remember, before we were just running this expression, we were getting 38 in the console. Well, actually, we can run this expression and place the x value that we've assigned the outcome of this expression to in this global environment that I mentioned before, but we didn't really cover anything relating to it. Okay, so that's basically how we get the x. We can even print the x to the console if we want, and it's going to produce 38. So that's just saying, go into our memory, find what we assigned to x, and please print it to the console. Okay. You can also do this horrific thing here, which I don't really like and won't be asking you to do it, but you can assign, and you see it's in the opposite direction. I know people do this in MATLAB as well, and it's just so, it's not how my mind works, and I'd quite like you not to do it, please. Please always assign things on the left-hand side, okay? So it still works like that if you want, but I'd much prefer it if you put the expression on the right-hand side and what you're assigning to on the left-hand side of the assignment operator. And I'm perfectly happy for you to use equals. So let's just give you an example. Test equals 2 plus 2, and test should be 4. Okay, so we can see it there that test is 4. And I think that arguably equals, if you're a Python user, would be a lot more straightforward than using this kind of arrow operator. But I don't mind which you use, it's perfectly fine. Okay, so now we're still on assignment operators. One of the cool things you can do is you can collect sequence of numbers and add them to an assignment operator. So here we've got a sequence of 1 to 20. You can see that as I've printed them to the console, and we can actually just assign that 1 to 20 to x. And if you put a semicolon, as we've got here, and then put an x again on the same line, you can actually get that x value printing to the console as well. I'm not so much of a fan of this. Normally I quite like an individual statement with an assignment operator, all on a single line, and then just start a new line and you can have a space and then it's super clear. So you can kind of see how I've written the code in this, so that you can see kind of how I prefer it to be. So obviously you can do this if you want, but I prefer it when it's kind of spaced directly after. In reality, you're not explicitly going to, in a full script, have this printed to the console and also being assigned like this on the same line. It's really just to show you what's happening here. Regarding the colon, that's basically meaning that what we want is all of the integers between 1 and 20. Okay, that's how we get this long vector of integers. Okay, so we covered expressions, we covered assignment operators, and now we're covering functions. So basically, I haven't covered it here, but you are able to use inbuilt functions, and you're able to make your own inbuilt functions. So let's just use a very basic one. So let's just take the square root, and for example here what we've got is the square root of 25, which is obviously just going to be 5, but it just gives you an example for how you're able to use an inbuilt function that's been specified. You know, most of the basic math operations like this will obviously be already inbuilt, but if you want to make your own function, we do that at some point, and you are able to literally do whatever you want. Functions are a really nice way to produce something which you may use repeatedly. So I think in code they say normally you'd never repeat yourself more than twice, maybe. Okay, so if you're doing something 3 times, then maybe you should think about getting a function for it, in which case then you can just have a nifty little kind of one-liner that you give a couple of pieces of data to, and then maybe it does some processing in your own bespoke function and returns a number once it's been processed as you desire. Okay, and it's handy because then you don't have, you know, maybe you want to make a change to something, how you do that calculation. If you then specify it out in 20 different places, you have to go and change 20 different places in your code. Whereas actually what you want to be able to do is just have one repeatable function, and then if you need to make a change to it, you can just change that one function. Okay. It's also much better for reducing the errors that you're inevitably going to introduce in your own code. So you don't want to be repeating yourself lots of times because you can't easily test it. What you want is really a function that you write, and this is a more advanced topic. I'm not going to be getting into it here, but basically you can write a test. So if your function says, I'm going to take A and take B, I'm going to add them together, you would just create a test which was like, A is 1 and B is 1, and the answer is 2. And that's truth, okay? And then we know that the function's working. But basically, that's a very kind of key part of software development, and making sure that your code actually does what it is supposed to do in the background. You don't have to worry about that, so that's a good thing. But I just wanted to make you aware of it because if I can, you know, portray code best practices as part of this module, then you're going to be a stronger job candidate as a consequence, because you're going to have a good understanding of what's kind of ideal and best practice from a kind of industry standpoint using this type of statistical modeling approach. Okay, I think that's fairly straightforward now. We've covered those 3 different types of data. Let's get on to data organization. So we can create a vector, which is just basically an ordered collection of numbers. Okay, so we can use this C here, which basically indicates concatenate, which is just a fancy way for saying put them together. So we can say concatenate the numbers 1, 2, and 3 and allocate it to Z, okay? And that's what this vector is here. It's a numeric vector of 1, 2, 3, okay? We can also create this, use this scan command. So what this is doing is saying it's going to accept numbers typed into the console. So here we can go 20, 30, 40, and you can just press enter. And then basically this B scan has entered as a vector up here with the 20, 30, and the 40, okay? So we can even press Control Enter there, and it's printing it to the console to tell us that it's got that 20, 30, and 40 in one single vector, okay? So if vector sounds complicated, just think of it as a single row in an Excel spreadsheet. It just has a name, which is the column heading, and then it just has a bunch of whatever you give it. It could be it could be numeric data. So just think of it as a row. It sounds fancy, vector, but it's not. So you can just think of it in this way. The good thing about vectors is then you can actually perform math on them and do different operations. Okay, so basically here, let's create this. Let me clear this so we've got a bit more space. So this just allows me to clear my environment, which I've done, and now it's clear. So let me just enter this vector v, which just contains 1, 2, 3, 4, 5. So it's a one-dimensional vector, or you can call it an array if you're more familiar with that, or just think of it as a column in a spreadsheet. And the point is I can go v multiplied by 2. Now you see what we have here is 1, 2, 3, 4, 5. When we times it by 2, it's basically saying, okay, give me 1 times 2, which is 2. Give me 2 times 2, which is 4. Give me 2 times 3, which is 6, etc., etc. Okay, so you can see how we were able to carry out this operation on this vector. We're also able to create another vector called W, which contains 10, 20, 30, 40, 50, and we're able to add them together, okay? And what this is going to do is it's going to go into V and W and find the first row in each, and it's just going to add those numbers together, okay? So if we do that here, what we have is we had the 1 and the 10, and that's produced 11 when we've actually added them together, okay? And we had the 2 and the 20, so it's 22 here, okay? So hopefully that makes sense to you. You're able to, for example, add vectors together, or you could do other operations. You could divide or multiply, whatever you want to do. But this gives you an indication of the flexibility of this programming language, which is very large. So that was vectors and how we basically kind of are able to manipulate them. We are also able to create lists. Now, lists don't just have to be numeric, they could be a collection of objects. Okay, so here I've created a list and it has a name for Sue, it has a name for Steve, and then we have an age for Sue, 39, and we have an age for Steve, which is 40, okay? We're able to create that list. You're able to add the list to the environment, you're able to click on it and look at the information that's in it. It tells you what type that information is. It's also printed it down here to the console. Now you're able to access parts of the list. So if we go my list square bracket 1, what it's basically done is it's gone into my list and it's found the first value that we have within that list, which is Sue, and it's printed it to the console, okay? You could also, if you wanted to, which was much preferable, rather than indexing by number here, which is basically saying just go to the first row in the list and get me that datum, that item of data, you could just say, look, just give me the item of data, the value of data, which is called her age. And this is really important because you could shuffle the list around by accident. It happens all the time, and then it produces the wrong data for you when you call it like this. So the beauty of doing it here, where we call this this item of data using the $, is it goes in and it just gets that one piece of data that you want, which is her age. Okay, so it doesn't matter where that item now is throughout the list, it's always going to produce her age because you've specified that particular item of data by its name. Okay, and that's going to be really key because once you get into the practical this week, you're going to have to get columns of data, and the way that you get those columns of data is by basically stating the $ and then the name of that column, and you're going to use that to subset your data. Okay, great. You can also create a data frame. So here we have X, which is going to concatenate 10, 20, 30, 40, 50. Let me just clear the environment. Click run, it's going to add X in up here, so we've got 10 to 50. And then let me do the same here, so we're going to click run again for Y, and it's going to add in A, B, C, D, E. And then we're going to create a data frame here, which we call XY, and data frame is a function. And what we're doing is saying, give me a column called numbers, and allocate the data as the X, and give me a column called letters, and allocate me the data as Y. Okay, so when we do that, we're then able to go into our data frame like this. You see we have a column called numbers, and we have the numbers down here as rows, and we have a column called letters as well, and we have all of those different letters running down the rows. Okay, so you can also print this out to the console if you want to inspect it that way. But I think that kind of rounds off how we're able to create vectors, concatenating different items of data that we have, which could be numeric data like 10, 20, 30, or it could be string data, so letters, for example, like A, B, or C. And then we're able to put them together into this data frame form. And I touched on data frames last week, so it's kind of a good way for us to bring this together here. It's just like a matrix, and you can think of it also like an Excel spreadsheet, and it gives you this structure of data. Okay, so this number here, 1, 2, 3, 4, is the index. That's basically the row number. We then have the numbers that we entered here using the X, and we have the letters entered here using the Y. Okay, Great, so just remember that I emphasized that we can access individual vectors by saying go into xy and get me vector 1. So this is the first column basically. This just gives us the first column. But I mean, we could do that also for the second column, so var2, this is going to be the letters. That's fine, but remember, please remember, you could shift the columns around or whatever, or manipulate the data frame, and then that way of accessing based on the number could produce the wrong data. So what I want you to do is I want you to go XY for the data frame, $sign. The $sign indicates you want a column, and then you're going to list the column by name, and that column by name is going to be letters. Okay, so now when we do that, we're able to get just that individual one. Doesn't matter which way you shuffle the data frame, you're always going to get exactly that one column that you want. We can also go directly into that data frame and give it basically like row, column coordinates and say, get me that one datum of information, okay, that one piece of information. So for XY, we could say, go to row 1, column 2, and get me that piece of information. So row 1 here, column 2 is A. So hopefully this will produce A when we run it. Yes, it does. And then for this one here, we say, go to row 3, column 1, row 3, column 1, we think it's 30, so let's hope that's going to produce 30. Yes, it does. Okay, and I always forget which way we index. Okay, so the way to do it is to remember it's like a map. You go along the x-axis and then you go up the y-axis. So you're first stating the row that you want to go down, and then you want to state the column. Okay. Right, so I hope I didn't confuse you too much there. It's you need to go down the row first and then select your column number. Okay, great. So let's move on to data sets now. So most of what we were doing before was basically stating our own data sets. We kind of creating them ourselves manually. We were inputting data manually. But very often we're going to want to use inbuilt data sets. Okay, so in R, if you type data curly brackets, what you're going to get is a list of all of the inbuilt R data sets. Okay, so there's quite a lot of them. Essentially, you could specify whichever one you want. So here's BOD, which stands for biochemical oxygen demand, and we've loaded it into our memory. And if you use help and then specify the specific name of the data set that you have, you can actually read about it down here in the help menu. Okay, so BOD stands for biochemical oxygen demand. The BOD data frame has 6 rows, 2 columns giving the biochemical oxygen demand versus time and evaluation of water quality. Okay, so once you've got BOD and it's basically in your global environment, you can look at the data here. So we've got time, we've got the biochemical oxygen demand here. There are 2 columns. We can even create a vector out of just the time column, for example, or we can do that for the demand. And what we end up there printing are those 2 different vectors that we've created from the data set. Okay, we can create a new data set if we want, called new BOD. Here we've got the time, we've got the demand. Okay, and this is our own data set. So that's just recapping on that one function that we used previously called data.frame, which is a really useful one for you to manually create your own data frames. And a trick is you can put the name of the function in help brackets and it will produce an overview of what that function does. Okay, so we will repeatedly come back to that because I will show you how to read up more on the functions that you have to use. So in the data that you downloaded, there should have been a data set called, I think it's rain, precipitation essentially. So you've got the Excel spreadsheet here, and it's basically rain for each year, the annual rainfall for DC and for Baltimore. This is in inches. Okay, So we need to read this, okay, which means we need to use the read.csv function. But before you do that, you maybe just want to take a look in the help menu, because it will give you a description of exactly what this function does, okay. Now the challenge is going to be when you use read.csv is you need to basically tell it where on your computer this data is. Now R does not specifically know, okay, so you need to basically specify in the code exactly how you get there. Now you can explicitly specify that file path. So I could go here, right click properties, this is on a Windows machine, and it tells me the location here. So if I really wanted to, I could manually explicitly state this file path to show me where the data is. Now the problem with that is when you change files or you swap files with other people, they're not going to be able to access the data in the same way because their machine will be named differently, the data will be in a different place on their machine, so it's not going to be easily exchangeable with other people. So I'm going to show you a nifty trick, and that's that if we install the package rstudio.api, we restart here. This little piece of code which I'm giving you basically says go to the RStudio application programming interface, get the source editor context and find me the path. Okay, so this is going to find the path where we're currently loading the code from. So my lab1.r code is in this directory which RStudio has been able to find, okay? And then when I combine it with this dir name, which is a function for directory name, basically what I'm able to do is say the current create this path here into a directory name, okay, and call it folder. And then when we do that, when we click folder and we type it to the console, we have that string that I manually produced before just by kind of finding it on my machine. Here I will just find it for us. So what this means is that when you download this code and you open it on your machine, providing you've saved the code and then you you install RStudio API and you create the folder this way, you can automatically produce that one single kind of one line of convenient magic, which is the folder from which you are operating from, okay? And this matters because once we've got this, we can basically say set the working directory. So this is a function, setwd, which you can look at in the help menu. And you can basically set the working directory for the current folder, okay? Which is great, because then it's like really easy for you to load in data from that one directory. Can you remember this is where I have the precipitation data, and this is what we want to load in? So we can create a file path now. So we have the folder, and let's say that we have a file name. We can even add it onto that folder structure so that when we just load in the data, we have a single one-liner which says go to my folder and then find my file name, load this data in. So this might be complicating things a little bit, so let me just hash that out. What you want to do is once you've set the working directory here, you just want to go read.csv, which means get the read function that we want for a CSV file. And then when we do file.path, what this is saying is get me the folder path and get me the precip.csv file name, put them together into a single string, and then give that to read.csv, okay? And when we do that, it reads in the rain data, okay? So this was the data that we had in the CSV file. Okay, I assume you are all familiar with CSV, so it's very much like an Excel spreadsheet, but an Excel spreadsheet is proprietary to Microsoft essentially, whereas a CSV file is something that can be commonly passed around in a very easy way. It's just data that's separated by a comma-separated value. Okay, that's what the CSV stands for. Okay, so you produce that rain, which is what we wanted to do. It's loaded in the environment. Let me just clear this up and load this in again. So go to folder, rain. Okay, there we go. So now we can plot graphics. So we can go to the help menu, and we can actually look at what the plotting option does. Okay, so there's a variety of different packages that can use plot. I'm going to show you basically how to plot things later in Ggplot 2, which is a more advanced graphical package, but it's better. Okay. So essentially, what we have here is we're saying we want to plot. We have the rain data, and we're saying go into the rain data frame and get me just the single variable called DC. Okay, so this is the number of inches that's fallen of rain in DC from 1950 to 2017, and we just have the DC portion of it. Okay. And we're able to plot it. So down here what we have is the index, it's just the row number, for example, and then we have the number of inches of rain. We're able to do the same for the year, so this is 1950 to 2017 essentially, and we have the row number as well, the index. We can then plot scatter plots. Okay, so by using the plot function here, we can say, okay, place the year on the x-axis and the rain on the y-axis, and essentially we're able to then create this type of plot here. So it doesn't seem to be any clear statistical correlation across this, any clear kind of time series trend. But essentially, once we've got that, we can start to create kind of more sophisticated plots. Okay, so plot always starts a new plot. The kind of plot that it draws depends on the first argument. We're able to actually change the type of plot that we use. So here we're specifying type equals L, and that's producing a line plot essentially of the rain in DC. Okay. Right, so we can also, if we want to create some funky colors for the plotting components within our plot. So for example, here all we've done is we've specified a title first, main DC precipitation, and then down here what we've done is we've basically given a color to the line that we plot, and then we've basically given a color also to the main title and a color to the other X and Y axis labels that we have. Okay, so nothing too complicated. And if I must say, this looks particularly ugly. So I'm not a fan of this type of inbuilt kind of very basic plotting. It's fine. I'm going to show you how to do it here, but I'm going to show you how to produce beautiful plots later on. Okay. So histograms. Now, you are, in your assignment this week, going to have to produce histograms and plots, okay? So you need to know how to do this. So if you just look first at help, a histogram basically, or at least this function is a generic function for hist, which computes a histogram of the given data values, okay? So a histogram is just indicating the frequency of values in your data set. So if I go hist rain, and that's the rain for Baltimore, so when we go rain $Baltimore, remember we're getting the column called BAL Baltimore. And basically what we're doing is we're plotting that, and this is the inbuilt function. It basically decides the width of the bins. So this is the width of the bins here that it thinks are most sensible. And it tells us the frequency as well on the y-axis. So for the values between 40 and 45, we probably have something like 18 values, okay? Right, now we can change the breaks. So remember me saying that there were like the widths of the bins here? We could have 70 breaks, which would create 70 individual bins, okay? Can you see now what we basically have is we have far fewer, far fewer number of values per bin, but we have way more bins, okay? And we even have plenty of bins that we're not even using. So this is a bit redundant for what we're trying to plot. But arguably, it's better than if you just had, for example, 2 breaks and you produce 3 bins, because this is basically this isn't really any use at all because you can't discern what's actually happening in the distribution of the data. Could look at 4 breaks, which is a bit better. I mean, that's fairly sensible. Now it kind of nicely aligns with every 10 inches of rain that we have, okay? So that's quite a nice way to do it, but I would probably prefer that we did breaks, say, every 5 inches of rain. That would probably give us a more kind of nuanced understanding. So we can look here at the histogram for the rain in Baltimore. We can say that we want 10 breaks, and we can say on the x-axis we want this to be limited to only between 30 and 60 inches of rain. Okay, so you can see we've basically ended up clipping some of the data points, so we don't have all of the distribution here. That's fine, it's just that it looks a bit sloppy. And sometimes you have to clip your distribution, but this isn't really particularly attractive. You could try to specify your intervals here, but we would get, on this particular case, an error because basically we end up having some data values that are bigger than this lower bin here of 60. Can you see we've got some over 60 over here, so it's failed. So if you're going to specify the number of breaks, you need to make sure that you're able to capture all of your data points, okay? So all the way up to the maximum value in the data set, like you have here, okay? So up to this, this 70. So next what we're going to have is basically the cumulative frequency. So basically this is a way that you're able to plot your data to show the cumulative absolute frequency line, which is basically indicative of where a certain number of scores fall above or below any sort of given value that you might have. Okay, so this sounds more complicated than it is, but I'm going to show you exactly what we mean by this now. So let me just plot. I'm going to sort all of the rain results that we get in DC, and we're going to do it for all of the number of entries that we have. Okay, so this is the cumulative frequency plot for the rain in DC, so from 30 inches here all the way up to 60 inches. And these are the number, this is basically like the row index essentially, so from 0 to 60, I think it's 68 values that we have, so just shy of 70. But they're all ordered, but what this means is that we know that 20 of the 60 values fall beneath 35 inches of rain per year, okay? And that's really kind of handy, okay? So you can arbitrarily find a point in the distribution and understand, say you want to understand where 50% of the values are, then that 50 percentage point is going to be just about here at the 34, row 34. And that's going to indicate that 50% of the time we have about 38 to 39 inches of rain in DC a year. Okay, so that sounds more complicated than it needs to be. If you're not sure, Google cumulative frequency plots. But what I really like about these is you can actually think of these in probability terms. So I've just converted this into a probability between 0 and 1. So basically that allows you to find the tail of the distribution, essentially, so the upper values. So you know that only in 1% of the times do you actually get more rain than, say, 54 inches, which is really handy. Okay, so if you're sat in New York and you are an insurer, then you need to be able to quantitatively estimate how often there's going to be extreme weather events, maybe related to flooding, maybe that's the line of insurance that you're in, and this type of approach is going to be able to kind of guide how often you might need to pay out, and therefore how to price your premium. Okay, great. So let's move on to just finishing this last part of the lecture. Okay, fantastic. Let's move on now to the low-level graphic commands. So this allows you to actually start to change some of those aspects of your plots, like the titles, the axes, the overlays, the points, the lines. As I will show you at the end of this lecture, I prefer you to use Ggplot 2 that I'm going to show you how to use, but I just need to make you aware that you can do this using the kind of very simple inbuilt packages. They just might not look as attractive as some of the the more fancy external packages which have been developed and which we're able to import into R using the code that I'm going to show you. Okay, so here I've just created another histogram, but that histogram, which is basically plotting the DC rain column, we've basically turned off the axis labels. If you don't provide a main title, you just provide the quotes like this, then there's basically nothing to report. And that's the same also for the X label and the Y label. So you get this rather odd shape down here, which obviously doesn't have any labels, which isn't very good. You can add a title back in. So here we've added title for the hist, and then we just type the main title is equal to the histogram of DC precipitation. Fine. You can also color it if you want, so you can just re-enter this col.main equals orange, and it's going to color the title. And you can do the same also if you want to color the other labels a particular color, such as blue, as we do here for the X and the Y labels. Okay, so when we do that, we end up with the frequency here on the Y-axis, precipitation on the X-axis, and then we have this rather unattractive bright yellow title here for histogram for DC. Okay, so that's just showing you the basics for how you change the graphics, some of the aesthetics associated with that. You can also change the entire graphics page layout, which is kind of a more advanced, kind of sophisticated way to do it. So you can have a long list of different graphical parameters that you want to change, and you can save them using a par function and then reload them whenever you want or swap them out. I'm not going to ask you to do this. I just want you to be aware of this. It's in the course, but I'm not going to explicitly test you on it. So it's just a way for you to maintain all of the overall graphical parameters for a particular page that you may be working on. Okay, so the par opens the graphics window and shows you the existing settings that are currently being used in your session, and then you're able to if you're able to change any of the defaults, then you could basically reset them whenever you want. Okay, so if I just execute the par, so remember it's Control-Enter, that's basically going to tell us all of this. It looks like gobbledygook, but it's not. It's basically giving you an indication as to how the margins are set up, what fonts are being used, all of these different kind of graphical aspects of the graphics that you might be interested in, okay? Now, we're actually able to save that if we just assign the par function to this. We're going to put it in our environment called old par. Okay, so we've assigned it to old par. And now all the defaults are stored. We can change the number of rows, for example. Okay, so this is going to say that we want 2 rows and 1 column. Okay, so we do that now. We just need to set the margins correctly, and now we can start to put in the 2 different histograms that we've already plotted essentially. So this is the histogram for the rain frequency in DC across all of those years, so it's 1950 until 2017 I think it was, and then we are going to do the same as well for Baltimore, and essentially what we're going to do is then going to put them into those 2 different rows. So we've got in the first row we've got the histogram of rain for DC, and then we've got the histogram of rain for Baltimore. Okay, so I think this is fine. It creates a reasonably nice looking panel plot, although I'm not going to explicitly ask you to actually produce it in this way. I'd rather you did it in Ggplot if you prefer. Okay, one thing I do want you to know is how to actually export a graphic like this that you've produced. So if you go here and you click export, you should just be able to export it as you normally would do. So you can click the size, you can click the directory that you want to save it to. Let's just call it test, and then we can save it there. And hopefully we have a test just here. There we go. And we've actually got it saved. So you can save it as a PDF like that when you have a graphic, or what you can do is you can just copy it to a clipboard. Okay, so copy to clipboard here. You can go to a Word document, and then all I'm going to do is you can press right click, paste, okay, or you can press Control V, which is just going to do exactly the same and paste it, okay. Or if you want to be really fancy, you can paste it as an independent bitmap, which sometimes gives you a higher quality graphic, but I think in this case it was already pretty low resolution before we extracted it. Okay, so there we go. That's just a bit of an indication as to how we export some of these graphics. When we have objects in the memory, so the environment up here, we can actually list them. So we have a folder just here as a value. That's the string of the path directory for the folder that we're currently active in, that we set the working directory on. We have the old PAR, so it's the old graphics interface that we just saved temporarily. And then we also have the rain data, which you'll be very familiar with, okay? And what we are able to do, if we really want to, is we can use RM curly brackets, and this allows us to basically just remove whatever we specify within this. So if we specify that, it just does exactly the same as this function up here, which is just to clear the environment, okay? So you can either specify it manually if you're writing a script and it's kind of handy just to remove certain things, or if you want to just clear the whole environment, you can just click clear objects from the workspace. Great, so we are on the home straight for completing this laboratory, and hopefully you will be happy to hear that news. So look, you can install Ggplot 2 if you don't already have it. You can just click install by running this code here. It's part of the tidyverse that I told you about previously, so it's Hadley Wickham's overall set of packages, and just one of them is Ggplot 2. It stands for the Grammar of Graphics. And then plot, obviously you're doing plotting with it, and then 2, I think maybe this is the second version of it that he created, I'm not sure why, but I know that he always says that you should have a very unique package name so that people can find what it is that you've produced on the internet very easily. So maybe the 2 was just because there was something already called Ggplot on the internet, so that just makes it, you know, slightly different from all of the other Google searches. Okay, so look, I've installed Ggplot 2 and I've loaded the package into my environment, all right? We have already been through this, so what we're able to do, because we cleared the folder when we used the remove function, was just to put the folder back into our environment here. So that's the folder that we're operating in. So the RStudio API finds the existing path, we take it as a directory name and we assign it to folder. And then we use that basically by saying, okay, use the file.path concatenation function, take the folder directory and take the name of my file, which is precip, so precipitation.csv, and then put them together and then read it in using the read.csv function here, okay, and then assign it to this name rain. And then we get exactly the same data that we've already plotted. So it's very, very simple. And then once we have that, we can start to play around with Ggplot. So I showed you a kind of cheat sheet for Ggplot in the first lecture, and I showed you exactly, I showed you a whole tile, and it's available in the course slides. It's one of the last slides I showed you in the lecture 1 in the first lecture. And it tells you the format of how you basically input data. So you put the data frame first here, and then AES relates to aesthetic, which basically means you're going to specify how you want to plot something within the graph. And here we're saying we want the x-axis to be the column DC, which is the rain for Washington DC over all of those time periods. Okay, and that's how you get this basic function for Ggplot. And then once you've done that, because there's lots of different types of graphs that you could create, you then basically need to add a geometry function. And here, the geometry function, so geom stands for geometry, is for a histogram. Okay, so it's saying geom_histogram, which is the function for creating a histogram. So you're telling Ggplot you want to plot using this data set, this data frame, you want to plot this column and you want to create a histogram out of it, and you want to use a bin width of 5. Okay, so we're going to create bins every 5 units. And then what we're going to do is we're going to add some labels. So let's see if this works first. There we go. So this is a kind of ugly version of what we plotted because it doesn't have any of the labels yet. You see we have a plus here, and we have the labs function here, which is going to take the title, the subtitle, and the X and Y axes. And I haven't added it in yet. You can add it in now if you want. I just wanted to check that it ran first. And there we go. Now we have something that looks reasonably nice. So we have a plot with a title, distribution of annual rainfall. We have a subtitle, and I put it as data for Washington, D.C., 1950 to 2017. We have the frequency on the y-axis of all of those data points per bin. And then we have the number of bins that we have, which we have 6 bins. In this particular instance, okay, and this is all covering on the x-axis the annual rainfall in inches, okay. And once you've got that, so if you allocate it here to DC, you can see it appears in our environment as an actual graphic. And then once we've got that, we're actually then able to export this. So I showed you how we do this before by using the export function. Now I'm going to show you how to do it using a more kind of sophisticated way. So this is actually writing in code for how we export this. So first we want to set the path. So we're going to use the folder that we have already used throughout this practical. We want to give it a name, so we're going to save it as a portable network graphic.png. So this is a graphic type of file, and we're going to give the file name histogram of rainfall in Washington DC. Okay, so when we basically allocate this to the path here, you can see the path has come up down at the bottom. Now we just need to give that path to ggsave, which is the inbuilt function for ggplot to basically save that one graphical object that you've allocated to it. And basically you can specify what units you want the size to be in. So here I've used inches, and we're using a width of 5 inches and a height of 5 inches, and we're using the dots per inch as 300. So this is basically the resolution. 300's pretty good, that's pretty high res. And basically then we click, we're going to save this. This prints the graphic and saves it to the file, and then basically we turn the dev off at the end. So basically what this is doing is saying create a PNG here of this particular size. It creates the PNG, and then it puts the graphic into it, and then basically it closes the image at the end. Okay, so if we just run this code here, it's run through each of those lines. Histogram of rainfall for Washington DC, just here. Okay, great. So that's going to be the final thing that you need to do for this practical, and you should now have all of the things that you need in order to succeed at the assignment this week. Okay, so read the chapter in the book. It's going to cover some of the things that I covered in the lecture, and then essentially I need you to run over this content in the practical so you understand it, and then everything that is required for you to succeed in the assignment is already in the practical. You just need to work out how to kind of translate it to a new problem. So you're going to be asked in the practical to produce a histogram. You're going to be asked to plot various pieces of data, and you just kind of have to work out how to find the right piece of the code that's already within the practical, and then basically apply it to the new data that I provide you for the assignment. Okay. So look, I hope that that's reasonably straightforward for you. I appreciate we've covered a lot of content. The first real practical is always a bit of a shocker for anyone who maybe doesn't have a really kind of existing background in R, and I understand that, and I'm here to help you. So please do reach out to me if you're stuck at any point. My only emphasis would be please don't leave it to the last minute. Okay. Fantastic. Well, thank you very much for tuning in, ladies and gentlemen, and I will see you all soon. Goodbye.